Okay, so back to, we just found temperature and pressure. They want us to find the heat in. Where does the heat in occur? Right? To find Qn. Well, first we have to know, where does the heat in occur? We go back to our diagram. It's a nice place to start. Where does the heat in occur? Right here. The heat addition occurs between states 2 and 3. It's a constant volume heat addition. Okay. That occurs between 2 and 3. All right? Okay. What is a good tool to find heat transfer? Pause if you need to, but guys, at this point in the semester, that's got to be a gag reflex. What is a good tool to find heat transfer? You should be yelling at your screen right now, first law, right? And make the people around you uncomfortable. You're yelling at your screen. First law, yes. Anytime you need to find an unknown energy, the first law is a nice tool. The second law will let you find an unknown heat, but we don't have a constant temperature, so it's a little trickier. But the first law, I think, works just fine. First law, from state 2 to 3. So what is the first thing we do to write a first law equation? You should be, again, yelling at your screen, Steve, draw the system. If not, you have some work to do. Your finals this week, you should know how to write a first law equation. Okay, so I've got this piston. We draw this inverted. Normally with a piston we would have boundary work. There's no boundary work in this case. Why? Why is there no boundary work between state 2 and 3, Steve? Why is there no boundary work? Well, because it's constant volume. There's no volume change between state 2 and 3, therefore there's no boundary work. So what does cross the boundary? Again, how do we write a first law equation? Draw your system, then draw all of the energies crossing the boundary. What do we have crossing the boundary? Heat. What type of system is this? Is it a closed system or control volume? It's a very important question. Is this a closed system or control volume? This is a closed system because there's no mass crossing the boundary. So we write a first law for a closed system. I've got heat in, and that's the only energy crossing the boundary. So it's positive, it's coming in. And that's equal to the change in the internal energy. That's U3 minus U2, final minus initial. We're going from state 2 to 3, so it's 3 minus 2. And that's my first law equation. All right, how do we find the internal energy change for anything? Well, it depends on your substance. What is our substance? It's air. It's an ideal gas. These are the questions you should be asking yourself. How do I find these U's? All right, well, what is my substance? And that will tell you. This is air. It's an ideal gas. Therefore, I'm going to use some ideal gas property to do it. Well, I've already made the cold air assumption. For cold air, I know the specific heat, C sub V. There's a reason I recorded that earlier. Qn is equal to m C sub V T3 minus T2. Okay, we're looking for Q. I know C sub V and I know T3. I don't know this and I don't know that. Yeesh. Okay. Which one do you want to start with? And normally in class I would say, all right, which one do you want to start with? And I'd let the class pick. Do you want to start with mass or do you want to start with T2? We got to find both of them. A lot of times people will probably say mass first because this is probably still on the board. So to find the mass, P1 V1 over T1 is equal to mR, meaning m is equal to P1, that's 100 kilopascals, over V1, that is 0.00, you said that's 3 zeros and a 6, 0.0006 cubic meters, that's V1, divided by T1, we've already said earlier that was 308 Kelvin, right? It was 35 C, which is 308 Kelvin, and divided by the R value, which we looked up earlier, 0.287. That is kilojoules per kilogram Kelvin. Now the kelvins go away. The kilojoules is kilonewton meters, and the kilopascals is kilonewton per meter squared. So on top I've got kilonewton meters, and on bottom I've got kilonewton meters per kilogram. So the kilograms goes to the top. I'm left with a very small number. I'm going to write it on the next line. So I'm left with kilograms as my units. You do need to be able to figure that out on your own, but in this case, it is kilograms. Don't just assume because it's the SI system everything works out. You guys have lost a lot of points on exams doing that. It does not always work out. You need to verify that. I'm not trying to be mean. I'm just trying to save you when you get to heat transfer and fluid mechanics and other classes like that. You've got to be good with your units. If not, you will really struggle later. I'm just trying to save you some heartache later. 0.00068, we'll say kilograms. You could go ahead, we could carry it out more digits. I'm just going to leave it there. Okay. Probably could carry it. It should probably carry 3 or 4 significant digits. I'm being a little lazy. All right. Got my mass. Steve, what the heck are we trying to do again? What are we trying to do? We're trying to find the heat in. Okay. So to find heat in, we know C sub B, we know T3, and I know now the mass. I just found the mass. How do I find T2? Ooh, how do I find T2? Well, this is the reason I go ahead and draw this stuff out earlier and say, here's what we know about the different states. Because at some point, you're going to hit this point where you're like, all right, I need to know T2. What do I know about state 2? Well, I know the volume is the same as volume at state 3, but what else do we know? Well, we know the entropy is the same at state 1. That tells me something. It tells me something very important. Yes, it does. Remember, earlier we did this for an isentropic ideal gas. The ratio of temperatures is related to the ratio of volumes to K minus 1. So let's say this. Let's say T2 over T1 is equal to V2 over V1 to the K minus 1. And this translates out into T2 is equal to T1, which I'm going to say is 308 kelvins. V2 over V1, no, I'm sorry. That is V1 over V2, right? You invert the other side. So if it's 2 over 1 here, it's 1 over 2 there. And this is a max volume over a min volume, so this is multiplied by the compression ratio, which I'm just going to write as 9.5. You could write R in there and plug it in later. That's 9.5. K is 1.4, so to the K minus 1 is 0.4 power. Let's see what we get there. All right. 9.5 raised to the 0.4 power multiplied by 308 kelvins. That gives me about 758 kelvins. All right. Page 4. What are we trying to do? We're trying to find Qn. To find Qn, I need to know the mass. I know C sub V, and I now know both temperatures. So the mass, we said it's a very small mass. Does that make sense? Yeah, it's air. It's a gas. Gas is not very dense. I have a very small volume of air, so it makes sense I have a very small mass of air. So 0.00068 kilograms. You can convert that to grams if you like, but then we're just going to have to convert it back, so I didn't. Multiplied by the specific heat. We said earlier that was 0.718 kilojoules per kilogram Kelvin, I think. It's not too hard to go look. Yeah, C sub B for cold air, 0.718 kilojoules per kilogram Kelvin. So that's M C sub V times the temperature difference. We said earlier T3 was 1968.7. That's probably too many digits, so that's okay. 1968.7 minus 758. You could go ahead and write the kelvins twice. I'm just going to factor it out and write it once. 1968.7. I do the inside the parentheses first, so I don't have to write parentheses in my calculator. Minus 758. That's going to get multiplied by 0.718, and that's also going to get multiplied by the mass, 0.00068. Qn is about 0.59 kilojoules. The air has a very low specific heat, so it does not take a whole lot of energy to increase the temperature a lot. And that's kind of what you're seeing there. I've got a very small amount of mass and a very low specific heat, so it does not take much energy at all to generate this temperature increase. If it was liquid water, it would take a lot more, because liquid water is like 4.2 kilojoules per kilogram. So if it was liquid water, it would take a lot more, even at this small mass, to get the same temperature change. But this is air, so very, very low mass and very low specific heat. All right. Steve, what else are we trying to do here? Well, let's go back and look at the problem. Got this. We got this. Found Qn. We also want to know the efficiency. Okay. How do we find the efficiency here? I want to know the thermal efficiency. Now, there's a simple way to do it. There's a very simple way to do it. By definition of the Otto cycle, there's this guy. This is the easy way, right here. This is a little more difficult, but something really cool happens with this. I'll see if we get, how much time have I got? I got 3 minutes. Okay, so we can do it the easy way. Let's do it, let's set up the more difficult way, because something really cool happens. The net work out divided by the heat in, because I know the heat in, right? This is a known quantity. Let's figure out the net work out, because that is going to be the work in, the work out minus the work in divided by Qn. Well, where does this occur? Well, the work out occurs during the expansion process. That's from 3 to 4. And the work in occurs during the compression process. We could go back to the diagram and see that. That occurs between states 1 and 2. And the heat occurs between states 2 and 3. Now, if you set up your first law, right, how do we find these works? Well, an unknown energy could be found through the first law. First law between states 1 and 2. What occurs from states 1 to 2? Well, you go from, again, that's work in, so you're going up here. And to do that, you're putting this work in. It's adiabatic, or at least it's isentropic from state 1 to 2. That means it's adiabatic and it's reversible. They're all reversible. So your work in is equal to, again, it's m, it's final minus initial, so it's U2 minus U1. So this is work in is equal to m c sub v T2 minus T1. And if you look at the first law, from 3 to 4, same thing, you got this piston. This time it's expanding. I'm going quickly. I'm trying to squeeze this into one video. I don't think I'm going to make it. Right? So to get this, you're getting work out. So it's minus work out is equal to m U4 minus U3. Well, if you distribute the negative sign, you convert that to C sub V's, it's going to be work out. Again, I'm going to distribute the negative sign. Move it over, so it's 3 minus 4. It's going to be m C sub V T3 minus T4. So what happens here is this thermal efficiency. Right? Here this is m C sub V T3 minus T4 minus m C sub V T2 minus T1. The work out minus the work in divided by the heat in. That's m C sub V T3 minus T2. And notice the mass and the specific heat goes away. This is T3 minus T4 minus T2 minus T1 divided by T3 minus T2. We'll come back and do it the easy way and finish it.